Today we're going to start the last chapter before the AP exam, Chapter 8, and we're going to learn about particle motion. So we need to review three key terms that we learned at the beginning of the year: position, velocity, and acceleration. So we need to remember that position tells us where a particle is, located, and we usually talk about it on the x-axis. And we'll denote it as x of t for the position. For velocity, we have to remember that velocity tells us two things. It tells us the speed and the direction the particle is moving. So how fast and in what direction. And then we have to remember that the derivative of the position gives us the velocity. And that when velocity is greater than 0, our particle moves to the right. And when the velocity is less than 0, it moves to the left. And then our third term is acceleration. Acceleration tells us the rate of change of the velocity, or how fast the velocity is changing. And acceleration is defined as either the first derivative of velocity or the second derivative of the position. And then we also have to remember that when acceleration and velocity have the same sign, the particle is speeding up, and when they have opposite signs, the particle is slowing down. But today we're going to more focus on, if we're given acceleration, how do we find velocity, and if we're given velocity, how do we find position? So we have to remember that velocity, if we go backwards, given the acceleration, is the integral of the acceleration. And when we take the integral of the velocity, we can get two possibilities. So we can either get displacement or distance. So if we think about a graph, and if the graph goes both above and below the x-axis, if it's both negative or positive, we have to remember displacement tells us how far the particle is from the initial position. And so for in the graph that I drew, the particle is moving to the right until we get to C, if this is V of t. And then it's moving left until we get to B. So we have to add the distance from A to C, and then we have to subtract the distance from C to B. So when we do displacement, we just take the integral from A to B of V of t dt, because it adds the positive area but subtracts the negative area. So just taking the integral gives us the net area, which gives us displacement. When we talk about distance, that's about how far the particle traveled. And so to do that, there's two possibilities. We can either take the integral, if we use our diagram above, of A to B of V of t, and then subtract the integral from C to B of V of t, because remember, this is going to be a negative, so we're going to have minus a negative, which gives us a positive. Or to just do it in one step, we can take the integral just from A to B, but we have to do the absolute value. And I actually made a mistake. This should be up here, the integral from A to C. So we're doing the positive area minus the negative area, which gives us them added together. But in one step, we can just take the absolute value of the entire area, and that will give us distance as well. And then the third type we want to know about is average velocity. And so to find that, we would take displacement, how far the particle moved from its initial position, and we divide it by the time. And just like when you think about it, distance divided by time gives me rate. So when we think about the average value in calculus, we're going to say the integral from a to b of vt dt. So that gives me displacement, and I'm going to divide by b minus a. So that's the formula for average velocity. Notice it's the same formula as average value, except now I'm using velocity instead of the original function. So now we're going to do a few example problems. So the first one says we have the velocity of a function from 1 to 4, and we want to find the time when the velocity is positive and the time when the velocity is negative. So we first have to figure out when does the velocity change sign. So by doing that, we set the velocity equal to 0. So we set it equal to 0, and then we factor. So this factors to t minus 5 and t minus 2. And then I set each time equal to 0, and I get t equals 2 or t equals 5. And notice we always want to look at our domain. 5 is not in our domain, so we're not going to worry about that. Then to figure out what's happening between 1 and 2 and 2 and 4, we can make a sign chart where we have v of t, and we put our 0 on there. And we're going to try values less than 2, and then greater than 2, but less than 5. So if you plug in 1 into your velocity function, we get out 4, so the velocity is positive. And if we plug in, we can plug in 3, we get out negative 2, so the velocity is negative, which means the particle is moving to the right. From 1 to 2, and I used a close bracket on 1 because 1 is still positive velocity, and it's moving left from 2 to 3. Okay, and same 2 to 4. And the same thing, you need a closed bracket on 4 because at 4 the velocity is positive as well. Part B says find the distance the object travels in each subinterval. So to do that, we can say the integral from, the first one is going to be 1 to 2. And we're going to do t squared minus 7t plus 10 dt. And we don't have to put the absolute value here because we know the area is always going to be positive. So you can put it there, it won't make a difference, but we don't need it. And then I'm going to use my calculator to integrate this. If you want to practice integrating by hand, you can, but you should get 11 over 6 when we integrate this using the calculator. And if you did it by hand, you should get the same answer. And then we're going to do the same thing from 2 to 4, and we're going to use the calculator again. So if we integrate that, we get, so if I don't put the absolute value, I get negative 10/3, and then I just need to remember to take the absolute value after, so it's equal to 10/3. Since in my subintervals the velocity is always positive or always negative, I don't have to put the absolute value sign inside the integral. You can, but you don't have to if you know the velocity is always positive or always negative. So these are my distance for each subinterval. And then it says find the total distance. So one thing you can do for the total distance is just either add the distance from the two pieces. So we would just add 11/6. So the integral from, we would say 1 to 4, and we would be doing the absolute value. Since we already know the two pieces, we could just say it's 11/6 plus the 10/3. for our distance travel, which gives us 31/6. Or we can also do this in our calculator. If we didn't calculate the subintervals and it's not easy to do, we could do this for the function. And if you put that in your calculator, you should get the same thing. But make sure that you put the absolute value around it. So I forgot the absolute value here. So it would have to be the absolute value. If it's not, then you would be finding displacement. But we want the total distance traveled. Which gives us, if you put in your calculator, 5.166 repeating, which is the same thing as 31/6. Part D of this problem says, what is the particle's position at t equals 4 if the starting position of the particle y was 3 feet? So to find the position, the new position, what we do is we take the initial position and then we add displacement. So if you think about it, if I start at 2 meters and then I moved -3 meters, I would now be at -1. So that's what we're doing. So we're saying, what is the particle's position at t equal 4 if the starting position of the particle was y equals 3 feet? So we know our time interval again is from 1 to 4. And if we do the integral from 1 to 4 of v of t dt, and we're not going to put absolute value because we're doing displacement and not distance, so we're going to put our function in again. And that gives us -3/2. And so to find the new position, we're going to take -3/2 and add it to our starting position, which was 3. And that gives us 3/2. And this should say x equals 3 feet because our function was x in terms of t. And then our last question for this part is, it says, what is the average velocity of the particle in 1/4? So we have to remember the formula. The formula said we take displacement and we divide by time. And that gives us average velocity. So we're going to take the integral from 1 to 4 of v of t dt, and we're going to divide by our time, which is 4 minus 1. And then if we go back to our slide before, we found the integral from 1 to 4 was -3/2. So we're going to take -3/2 and we're going to divide by 3 to get our average velocity. And then we get -1/2. Now they might also ask us like a mean value question with average velocity. So they gave us our velocity function and they said find the value for t equals x for which v of c equals the average velocity from 2 to 11. So in this case, we're going to take the integral. We're going to find our average velocity first. So we're going to take the integral from 2 to 11 of our function. And again, you can use your calculator, calculate this to save time. And when you do that, you get 261. And then to find average of value, we divide by the change in time. So the change in time gives us 9. So we're going to do 261 divided by 9, and we get 29. So that's our average velocity. Then it says find a value for t equals x for which v of c equals the average velocity. So we're going to plug in, or we're going to set our function, and this should say t equals c. We're going to let our function equal our average value, and then we're going to solve it. So I'm going to set it equal to 0. And since we can't factor this, we would use the quadratic formula. So we'd have negative b plus or minus the square root of b squared minus 4ac all over 2. And again, you could use your calculator to save time, but make sure you know how to do this. And when we plug that in and evaluate that, our answers are either 8.645 and t equals 3.3542. And since we're looking in the domain of 2 to 11, both of these answers are possible. So it's saying, where does the function have this height of 29 of average value? And it's at 8.645 and 3.342. So you could graph this function, graph y equals 29, and make sure it intersects at these t values to make sure it's correct. Now you need to get out the worksheet that you got yesterday or today in class from the substitute. And so it should say exploration 10-2A, finding distance from acceleration data. And we're going to do this worksheet together, and then you're going to do the back of it, the average velocity for homework, as well as a few other worksheets. So this says we have a table, and it says the following table shows acceleration of a moving object. And so we have the time and the acceleration of this different times. So number 1 says assume that the acceleration changes linearly in each 10-second time interval, and the velocity at t equals 0 is 3 meters per second. Show how the velocity may be calculated at time t equals 10. So remember, if we have acceleration, to find the velocity, we're going to take the integral. And since we have a chart and it says we move linearly between them, these values, if you would plot them, it's going to make like a trapezoid. So to find the integral, it's a definite integral, we're going to find the area under the curve using trapezoids. So for each time interval, we're going to use a trapezoid to calculate the area. So for the first one, I know that we're going to do 1/2. The base is the distance between the time, which is 10, and then I'm going to add my two heights, which is 5 and 12. And if I multiply that out, I get 85. Okay. So that's my delta V. My change in velocity is 85. But they told me that the velocity at time t equals 0 is 3 meters per second. So I have my velocity, and this is 3. So to get my new velocity, if I started with 3, and I am now going 85 miles per hour, my new velocity is 88. So this is same as displacement. To find the final position, you have to add your original velocity to it. So if we do between 10 and 20, we would do 1/2 times 10, and then we do 12 plus 11. And we would calculate that to get what the change in velocity is, which is 115. And then we add it to our original velocity, which is 88, and that gives us 203. And we would do that for each one. For each time interval, you would have a trapezoid, and you would find the area. So you should finish calculating the average velocity and the velocity, and your end result, if you do it correctly, should be negative 100 for the change in V, and negative 112 for your final velocity. So you should finish those for homework tonight and then check your answer to make sure you get that. Then the second part, so we did this. In the table above, put a column showing the velocity at the end of each 10-second time interval. And then it says assume the average velocity in each time interval is the average of the velocity at the beginning and the velocity at the end of the interval. And assume that displacement is 0 when t equals 0. So now we're going to do displacement, and this is 0, and show how the displacement may be calculated at time t equals 10. So this is going to be the same idea. When we have the average velocity is from the beginning and the end, we're going to do the area of the trapezoid again, but now we're going to use the velocity. So like for our first displacement, we're going to take 1/2 times the width again, which is 5, or which is 10, and then we're going to do 3 plus 88. And if we work that out, you get the change in d, the change in the displacement, or the actual displacement, is 455. And then if I add it to its initial position, we're then at 455. So if you look on the next slide, it says in the table, put a column that shows the displacement at the end of each 10-second time interval. So that's what we're going to do here. So again, for the next one, I would do 1/2 times 10, and then 88 plus 203. Which gives me 1,455. So that's my change in the displacement. And then I would add that to 455 to get my new position, which is 1910. So you're going to do that until the end, and your final distance would be 6,155. So you should finish that up as well and make sure it's correct. Then on number 5, it says explain how you can tell that sometime between t equals 0 and t equals 60, the object stops and begins going backward. So if we look at this, we know that the function is going to go backwards when the velocity is negative. So you would have to look at your chart, and in somewhere here, your velocity should be negative. So we can obviously tell at 60 it's negative 112. So you need to explain in number 5 that the velocity changes from positive to negative. And then also the displacement decreases, which means I'm going to be adding a negative number. At some point. And then number 6 says, does the object go far enough backward to go back beyond its starting point? So its starting point is at time t equals 0. So in order for it to go back behind it, it would have to have a negative numbers on the number line. So no, because the displacement is not negative. Okay, so for homework tonight, what you're going to do is you're going to do the Exploration 10-3A, which is on the back of this Exploration 10-2A. You're going to finish the chart for Exploration 10-2A. And then in the packet of worksheets you are going to work on worksheet number 1 and worksheet number 4. And you're going to have a daily check on those definitions, so make sure that you do that worksheet and you remember them, because you're going to be working alone on that daily check. And then if you want to get ahead, you can start working on some of the practice problems with the graphs and the tables. And don't forget that the quick quizzes and the homework on the calendar from last Thursday is due on Friday as well.